What specific problem does the drag-and-drop LLMs (DND) method aim to solve in the context of parameter-efficient fine-tuning (PEFT)?
The drag-and-drop LLMs (DND) method aims to solve the inefficiencies associated with parameter-efficient fine-tuning (PEFT), particularly the high computational costs and the need for task-specific optimization runs. Traditional PEFT methods, such as LoRa, require extensive training on new tasks, which can be a significant bottleneck for practitioners deploying models at scale. DND addresses this by directly generating task-specific weights from raw prompts in a single forward pass, eliminating the need for gradient descent and per-task optimization. This approach not only reduces adaptation overhead by up to 12,000 times, but also enhances performance on unseen datasets by up to 30%. Ultimately, DND transforms the adaptation process into a more efficient and user-friendly mechanism, making it accessible for broader applications.
How does the proposed method DND work? Illustrate the process step by step from prompt batch input to LoRa adapter generation.
The proposed method drag-and-drop LLMs (DND) operates through a systematic process that transforms prompt batches into LoRa adapter generations. First, a dataset is divided into non-overlapping prompt batches, and corresponding trained LLM checkpoints are identified. Next, a pre-trained text encoder extracts embeddings from these prompt batches, which serve as inputs for the parameter generator. The generator, structured as a cascaded hyperconvolutional decoder, then processes these embeddings to produce task-specific LoRa updates for each transformer layer. Finally, during inference, DND can generate tailored model parameters for novel datasets in a single forward pass, effectively bypassing the need for traditional task-specific training.
Can you provide a simple yet illustrative example demonstrating the inner workings of DND, explaining how it generates task-specific parameters from raw prompts?
DND operates by first sampling a batch of raw prompts from a dataset, which serve as the input for generating task-specific parameters. For instance, if the task involves common-sense reasoning, DND would take prompts related to that domain and extract their embeddings using a pre-trained text encoder. These embeddings are then fed into a cascaded hyperconvolutional decoder, which generates the corresponding LoRa updates for each transformer layer in a single forward pass. This process effectively bypasses traditional fine-tuning methods, allowing DND to produce tailored model parameters rapidly and efficiently. As a result, DND can adapt to new tasks without requiring extensive training, demonstrating its drag-and-drop capability by generating high-performing parameters even for unseen datasets.
What are the theoretical or practical benefits of using the DND method compared to traditional LoRa adaptation techniques?
The DND method offers significant theoretical and practical benefits over traditional LoRa adaptation techniques. Firstly, DND eliminates the need for task-specific training by directly generating task-specific weights from raw prompts, which drastically reduces adaptation overhead by up to 12,000 times. This is achieved through a single forward pass, contrasting with LoRa's reliance on gradient descent, which is computationally expensive and time-consuming. Secondly, DND demonstrates superior performance, yielding up to 30% increased accuracy on unseen datasets compared to traditional LoRa's, showcasing its effectiveness in zero-shot scenarios. Additionally, DN's architecture, which combines a frozen text encoder with a hyperconvolutional decoder, allows for seamless scaling across different model sizes, enhancing its versatility. Overall, DND not only streamlines the adaptation process, but also enhances performance across various tasks, making it a more efficient and robust solution.
How is the effectiveness of DND validated in the experiments described? What datasets and metrics are used to demonstrate its performance?
The effectiveness of drag-and-drop LLMs, DND, is validated through comprehensive experiments across various tasks, including common-sense reasoning, mathematics, coding, and multimodal benchmarks. The evaluation involves both in-domain and cross-domain scenarios, where DND generates tailored model parameters from prompts of novel datasets not seen during training. Performance metrics include accuracy comparisons against traditional LoRa adaptations and foundation LLMs, with DND demonstrating up to 30% increased performance on unseen datasets and surpassing the accuracy of foundation models across all tasks. Specifically, the experiments utilize datasets such as ARC-C for common sense reasoning and other relevant datasets for math and coding tasks, showcasing DN's robust zero-shot learning capabilities. The results indicate that DND not only reduces adaptation overhead significantly, but also achieves superior performance, validating its effectiveness as a novel parameter generation approach.
What limitations or drawbacks does DND have, particularly regarding its reliance on prompt quality or representation, and how might these impact its generalizability to various tasks?
DN's performance is heavily reliant on the quality and representation of the prompts used for generating task-specific parameters. The method requires effective embeddings that capture the nuances of the prompts, which can be challenging given the semantic variation in linguistic inputs compared to simpler binary embeddings. If the prompts are poorly constructed or lack sufficient detail, the generated parameters may not accurately reflect the task requirements, potentially leading to suboptimal performance. Additionally, while DND shows impressive results across various tasks, its generalizability may be limited if the prompts do not adequately represent the diversity of tasks or domains it encounters, as the model's ability to adapt hinges on the richness of the input descriptors. Thus, the effectiveness of DND could diminish in scenarios where prompt quality is inconsistent or insufficiently informative.